Hi guys, this is a video solution for example tutorial sheet 7, which is about using functions in R and simulation and how to simulate from them. So as usual, I will go through this sheet command by command and also do the exercises. Okay. So let's start. Okay, the first thing you need to do is to open the R window. Right, this is the R window. Okay, and right, you should go to the course website for week 7. We are currently on week 7. There are 4 R functions. There are 4 R functions. If you just click on this link, you will get this. There are, as you can see, there are 4 functions here. The first one is called new f.1, the second new f.2, then new f.3, and finally new f.4. So let's start with the first one. Now what this does is the following. Let me try to explain it. Before that, let me copy this. Copy, and then excuse me. Let me copy this and paste it under the R window. Right, now let me explain what this function does. So you may suppose, sorry, so let me use the number key. Suppose you have a random sample x1 to xn from a normal distribution with mean equal to mu and standard deviation equal to sigma. Now, one of the things we learned in the course is, especially if you guys had looked at the video on chi-square distribution, one of the things I taught you is that under this assumption, the following: n minus 1 s squared, where s squared is a sample variance, divided by sigma squared. This guy here has a chi-square distribution with n minus 1 degrees of freedom. All right, this is one of the results I talked about on the video on chi-square distribution. So what this function here does is it simulates a sample of size n from a normal distribution with mu equal to 0 and sigma equal to 1, and then it computes this quantity here. It computes n minus 1 times the sample variance divided by sigma squared. And this is assigned the value ss1, and it returns ss1, right? So what I'm going to do, first thing I'm going to do is to generate values of this, generate values of n minus 1 s squared divided by sigma squared, and see what kind of distribution they have. Right? They should, I mean, theoretically speaking, they should have a chi-square distribution with n minus 1 degree of freedom. All right, so let's do that. Excuse me. So the first thing I'm going to do is, so new f 1 with n equal to 50. So I'm taking the n, the sample size, to be, so let's take it to be 20 to start with. Take it to be 20 first, all right? Then I'm going to do a histogram of the simulated data. Okay, with frequency equal to false. So this is the kind of histogram that you get. All right. Now on top of the histogram, I'm going to plot the density of a chi-square distribution with n minus 1 degree of freedom. So in this case, n is 20, so n minus 1 is 19. So, all right, so in order to compute the chi-square PDF, we need to define x values first. So let's take a sequence of values, say from 15 to 95 in steps of 0.5. Okay, then I will compute C19, which is the density of the chi-square at xp with degree of freedom equal to 19. All right, now I'm going to use the lines command to plot the PDF of chi-square on top of the histogram. It's going to be line xv C19. So you see, it's not a bad fit. I mean, it looks okay. I mean, it looks, the fit looks pretty good, right? Okay, so right now let's do this. Let's do the same thing. Now, here I took the sample size n to be 20, right? Now let's take it to be say 50, right? Okay. Then do the histogram again, all right? And let's define the xv values from 20 to 80. So let's say it starts from say 20 to 80 in steps of say 0.5. Let's compute C. Here the n is 50, so the n minus 1 will be 49. Okay. All right, and finally do the lines command. Oh, sorry, excuse me, it should be 49 here. All right, you see. So once again, the fit is pretty good, as you can see, right? The fit of the chi-square density on top of the histogram of the simulated data. And they should, according to the theoretical result, right, the simulated distribution of this, right, should approximate the chi-square distribution. All right. Finally, let's take n to be 100. Right. So do the histogram again. Okay, and let's define xv to be to range from say 60 to 140. So maybe say 50 to 150. So let's take it from 50 to 150 in steps of 101. And now the degree of freedom, because n is 100, n minus 1 will be 99, right? So let's call this C99. Now if you do the lines, this is what you get. So once again, the fit is pretty good, okay, as you can see. All right, so this exercise is on trying to simulate values of this statistic, right? Right, and draw a histogram, and on top of the histogram, we have plotted the density of a chi-square distribution with n minus 1 degree of freedom. So as you can see from the three plots, right, I have done, the three plots I have done, in each of the three plots, the fitted PDF approximates the histogram pretty well, okay? So that's the first exercise. Now to do the second exercise, let's go back to the course website, this one, right? So the second exercise relates to this function here. Excuse me. It's this function. Now, all right, let me copy and paste it here. Now, what this function does is the following. So suppose, let me use the number. All right, this is a comment, right? So suppose you have data x1 to xn, right, from a normal distribution with mean equal to mu and standard deviation equal to sigma, right? Right, and okay, the function computes the following. The function computes the sample mean, which is the x bar, and also it computes the sample median, right? And so there are two values. So the sample mean is computed by this command here, all right, and the sample median is computed by this command here, right? And it returns the sample mean and the sample median, right? Now the purpose of this exercise is to look at the distribution of the sample mean and the distribution of the sample median for different values of n. All right, so let's start with n equal to 30, right? Okay, now for this, I'm gonna simulate, right, with n equal to 30, right? And let's call this rest2, right? Okay, right. Then I'm gonna do a box plot of rest2. So this is what you get. So you see here, this is the box plot for the sample mean, and this is the box plot for sample median. So what this command here, what it has done is, it has done it's computed values of the sample mean and the sample median with n equal to 30, right? Okay, and it computed excuse me, just a minute. It computed 500 values of sample mean and 500 values of sample median, right? Each with n equal to 30, right? So it generated 500 samples with n equal to 30 and computed their sample mean and also computed their sample median. As you can see from the box plots, the box corresponding to the sample mean is a little bit shorter compared to the box corresponding to the sample median. So maybe in this case, you would prefer using the sample mean to the sample median, right? Now let's do the same thing with different value of n. Let's take n to be, say, 100, or let's say 50 to start with, okay? In this case, the picture is similar. Again, the box corresponding to the sample mean is narrower compared to the box corresponding to the sample median. Now let's take n to be, say, 100. Sorry, 100, I mean. Right, then you get this, the picture is similar. And let's say n to be, say, 200. In this case, the picture is similar again. The box corresponding to the sample mean is narrower compared to the box for sample median, right? Okay, now another result that I mentioned in the lectures, in one of the videos, I mentioned that if you have a random sample from a normal distribution with mean mu and standard deviation sigma, then the sample mean is also normally distributed with mean equal to mu and standard deviation equal to sigma divided by root of n. I hope you guys remember this. This is a result I mentioned. It's one of the properties of a normal distribution, that if you have a random sample from a normal, then the sample mean, all right, is also normal with mean equal to mu and sigma, standard deviation equal to sigma by root of n, right? Now I'm going to see, using the simulated data, I'm going to see if this actually holds. I mean, it should hold. Theoretically speaking, it should hold, right? So let's see what happens, all right? All right, now let's take a simulated sample with n equal to 30, right? Okay, the first thing we want to do is to draw a histogram of the simulated data, right, with frequency equal to false. Excuse me, sorry. We need to pick the sample mean, which is $x bar, right? Okay, so this is the histogram of the sample means with n equal to 30, right? Okay, now what I want to do is I want to plot on top of the histogram a normal density with mean equal to mu and standard deviation equal to sigma pi root of n. So to do that, first I need to define the x values. So let's define, say, xx to be a sequence from minus 0.6 to, say, 0.8 in steps of, say, 0.1. So it's from minus 0.6 to 0.8 in steps of 0.01. All right. Now that just defines the values along the x-axis. Then I want to compute the density, right, of the normal distribution at the values xx with the mean equal to mu, which is the mu was taken to be 0, which is corresponding. I mean, mu was, and the sigma is sigma. So the standard deviation is sigma by root of n. So it's 1 divided by root of n, which is square root of 30. Okay. All right, because if you look at the function, right? If you just go above, you see we took mu to be 0 and standard deviation to be 1. So that's sigma equal to 1, right? So for the sample mean, your mu will be 0, your standard deviation will be 1 divided by root of n. So 1 divided by square root of 30, all right? Then you do the line plot of xs versus den. And this is what you get. You see, so the fitted normal PDF, right? So it fits the histogram pretty well, as you would expect, right? Because that's the theoretical result. So, right. So this is with n equal to 30. Now let's do the same thing with, say, n equal to a different value for n. Let's say 100. All right. The first thing we want to do is do the histogram. Okay, the histogram looks like this. Then you define the x values, say so the x values go from minus 0.3 to plus 0.3. So it's minus 0.3 plus to plus 0.3. And then you compute the density at mu equal to 0, so mean equal to 0, and standard deviation sigma by root of n. So it's 1 divided by root of 100, okay? So this is what you get. So once again, you see that the fit of the normal PDF is pretty good to the histogram. And finally, let's take n to be, say, 200. Right, in this case, the histogram looks something like this. Right. Define the x values, say, to go from minus 0.2 to plus 0.2. And define the density values, mean equal to 0, standard deviation sigma by root of n, which is root of 200. And finally, the lines. So again, you see that the normal PDF fits the histogram pretty well, okay? So this is the exercise involving the second of the 4 functions. Now the third of the 4, let's go back to the course website. All right, so we've done the first 2 functions. Now this is the third one. Let's copy this and paste it here. All right, let me show you what this actually does. What it does is it's suppose you have a random sample x1 to xn from a Poisson distribution, right, with lambda equal to 10. Right, okay, now what the function does, it computes the sample mean, the sample median, and also the sample variance. So these are the three commands. This command here computes the sample mean, and this computes the sample median, and this computes the sample variance, right? All right, so all this for a sample simulated from a Poisson distribution with lambda equal to 10. And this is done 500 times. So if you take, say, for example, if you take n to be, say, 30, for example, right? It will do this 500 times with n equal to 30. So that it will simulate a sample of size 30 500 times, and it will compute the mean, the median, and the sample variance each time. Right. So what I'm going to do is I'm going to show you the distribution of these three guys, right, for different values of n. So let's start with, say, n equal to 30. So and let's call this S3, right? Okay, and then you say box plot of S3. This is what you get, you see. So there are three box plots. The first one is for the sample mean, the second for the sample median, the third is for the sample variance. All right, so it tells you how they are distributed, right? So looking at these three box plot, you see that the sample variance has large variability. So it's not probably a good estimator of anything, but the sample mean has the smallest variability in terms of the length of the box, and the sample median is kind of in between the two, right? So if you have to pick one of these, you would pick the sample mean, right? Because that has the shortest box. I mean, the shortest box means less variability, right? Okay. So remember that for a Poisson distribution with lambda equal to 10, right? The mean, the expectation, the variance are both equal to lambda. So if you are to estimate lambda, you would go with the sample mean, right? Because that has the shortest box, right? Let's do the same thing, say with n equal to, say, 100. Sorry, 100, I mean. Here you have this, right? Here, once again, the sample variance has a large box. The sample mean has this one. The sample median is kind of weird. The reason it looks kind of weird is because you may recall that the Poisson is a discrete distribution. So the values it can take are integer values, right? So the sample median, right, by definition will also be integers or half integers, right? So that's the reason it looks kind of weird, right? Because it's bound, by definition, it's bound to take values, integer values or half integer values. So that's probably not a good reason not to choose median. So again, in this case, you would go with the sample mean, right? Because the sample mean doesn't need to be an integer, and lambda, as you know, can take any real value. I mean, lambda in the Poisson distribution can be any real value, right? So once again, for that reason, you would go with this one. You would prefer, of the three, you would prefer to choose the sample mean, all right? Because number one, this box is pretty large. Number two, the sample median is bound to take values, integer or half integer values, which may not be realistic because lambda can be any value. Lambda can take any real value. It doesn't need to be an integer or half integer, right? All right, and finally, let's say take n to be say 200 and do the box plot. This is what you get. So you get something similar. Again, this one is weird because of what I just said, right? So once again, if you are to pick between the three, you would pick the sample mean, right? Okay, because one, the variability of this box is huge compared to the other two. Number two, the sample median is bound to be an integer or half integer, whereas lambda can be anything, right? All right, so that's the third function. Now, the last function is this one. Excuse me. So let me copy this, right? Let me copy this last function. Okay. And paste it here. Okay, so let me explain what this function does. So basically, it does, suppose you have a random sample, say x1 to xn is a random sample from a binomial distribution with n and p. Right? Now, what this does, it computes the sample mean, right? So the function computes the sample mean, which is given by this statement here, right? So it's just the sum of the x's divided by n, right? Okay. Right, now what I'm going to do is I'm going to run this function and see what kind of shape the sample mean takes, right? Okay, so let's say let's take n to be say 100 and say p to be say 0.1. All right. What am I doing? N to be 100 and p to be this, and let's call this res4, right? Okay. If you look at the box plot, it looks kind of symmetric, right? Because the median is about halfway between the lower and upper quartile, right? So it looks kind of symmetric. But we like to, in this case, I don't want to use box plot. I want to look at the histogram. The reason being is the following. You may recall that one of the properties of the binomial distribution that I give you in the class is the following, that if you have a random sample from a binomial, right, then the sample mean, right, can be approximated by a normal distribution with mean equal to P, right? P is the probability parameter, and standard deviation equal to square root, or let me write it like this, P times 1 minus P divided by N, the whole thing power half. Right, so okay, so this is a result I mentioned, I explained. I think I gave a proof of this result using the central limit theorem in the class. If you look at the video on the binomial distribution, you will see a proof of this, where when you have a random sample from a binomial, the sample mean can be approximated by a normal distribution with mean equal to P and standard deviation equal to the square root of P times 1 minus P divided by N, right? Now I want to check this result, right? In order to check this result, I'm going to simulate from this function and draw a histogram, right? And then on top of the histogram, I will plot the density of the normal, right? Okay, so let's do that. So I'm simulating n equal to 100. So I draw a histogram of the simulated data. So it looks something like this, right? So the next thing I want to do is to define the x values. All right, so the x values go from 0 to 0.2. So let's say sequence from 0 to 0.2, say in steps of say 0.01. All right, now I'm going to compute the density values of the normal distribution at the x values. So I use the function dnorm at xx with mean equal to P, which is 0.1, and the standard deviation equal to P times 1 minus P divided by N, which is 100, right? Okay, so that's the density of the normal distribution. And finally, I use the command lines to plot the density on top of the histogram. So this is what you get, but I made a mistake here, as you can see. The mistake I have made here is that when I did the histogram, I should have used frequency equal to false. So let me repeat it again, just to be careful. I should always use frequency. I mean, when you want to compare with the density, you should always have frequency equal to false. Okay. All right. Now you can see it's a good approximation, as you can see. Right. All right. So the fitted normal PDF, right, approximates the histogram pretty well, right? Now let's try this with the different value for P. Now suppose simulate with n equal to 100 and P equal to 0.6, then draw a histogram of it, right? And then compute the x values. When you do the density, the mean should be P, which is 0.6, and the standard deviation should be the square root of P times 1 minus P divided by N. And finally draw the lines so you can see how good a fit it is, right? All right, now let's repeat this with n equal to say a different value for n, say 200, right? Okay, so let's start with n equal to 200 and p equal to say 0.1, right? draw a histogram of it, which looks like this, and define the x values. So the x values say go from say 0.05 to 0.15. Okay, and then define the density values with p equal to 0.1, right, and n equal to 200. And finally, plot the lines. So you see one more time the fit of the normal PDF is good, right, not bad. And finally, let's choose n to be 200 and p to be 0.6. Draw a histogram and take the x values from 0.5 to 0.7 in steps of 0.01 and compute the density values. So this time your p should be 0.6, right? And finally do the line, right? This is what you get. So as you can see, once again, the fit of the normal distribution on top of the histogram is good. So this is what you would expect for large values of n, because remember this result here is an approximation, but if n is large, in the simulations we took n to be 100 and 200, which are pretty large. You would expect this to be a good approximation, as you saw in the plots, right? So this completes the four function, the illustration of the four functions, okay, and also completes the solution of the video solution of tutorial sheet 7.